We present our work on deep lighting environment map estimation from spherical panoramas. Lighting estimation is an important task for compositing synthetic content for visual effects or augmented reality where the synthetic content can be realistically lit. But lighting estimation is a challenging inverse rendering problem that is highly under-constrained, and none of the Hadamard-Well positiveness criteria apply. It also needs to be estimated in high dynamic range, typically from low dynamic images. Modern data-driven methods are a promising way to address challenging inverse problems. Deep light regresses HDR lighting by estimating a low-resolution probe image from a single monocular low dynamic range image acquired by a mobile phone. Guerin et al. On the other hand, offer localized estimates and regress a fifth-order spherical harmonic representation. Similarly, in neural illumination, a spherical illumination map is regressed from a single perspective image and a location on it that represents the lighting arriving from all directions to that location. Finally, Gardner et al. Take another direction by regressing parametric lights in a scene that allow for finer-grained lighting of synthetic objects. Yet, all these works aim at inferring a scene's lighting from a single perspective image, limiting their applicability to spherical images. For data-driven spherical lighting estimation though, we first need to overcome the lack of data availability. Manually capturing spherical panoramas using customized rigs and light probes is tedious and would require special post-processing to remove the probes from the images afterwards. The Laval HDR dataset of Gardner et al. Was created by using bracketed captures and then estimating the corresponding HDR images. Still, the manual collection process resulted in less than 2000 LDR-HDR image pairs. Consequently, some methods use synthetic data that allow for highly accurate ground truths, but are plagued from the synthetic to real domain gap. Another recently introduced approach warped perspective HDR images to generate panoramic HDRs, coupled with corresponding warped LDR images. Yet, the warping process introduced severe distortions and high-frequency artifacts. Still, the Matterport 3D dataset offers a large corpus of indoor spherical panoramas with coupled geometry information in the form of spherical depths and normal maps. It cannot be used directly for lighting estimation though, as the LDR panoramas come with pre-baked lighting, while no spherical HDR panoramas are available. At the same time, utilizing the perspective HDR images to create spherical ones produces severe warping artifacts, with other significant drawbacks being overly saturated HDR images and missing lighting information. The only available dataset with coupled LDR and HDR spherical panoramas is the Laval Indoor HDR dataset, but it has a limited size for modern data-driven methods, without around 2000 samples. Our concept relies on coupling these uncoupled datasets and overcoming their limitations. We achieve this by employing image-based relighting, exploiting the availability of high-quality HDR information from the Laval dataset and the content plurality and multimodality of modern datasets, like Matterport 3D. The Matterport 3D images were captured in real-world environments and already contain the original scene's lighting information, while the Laval HDR images provide standalone lighting information from different scenes. After relighting the Matterport 3D images with a new lighting, we feed them into our model that estimates the scene's lighting parameters. As long as we can condition our supervision on the newly imposed lighting alone, we can train the model to estimate lighting from a single monocular LDR panorama. This concept crucially relies on a global Lambertian assumption for the original image and scene. This widely used assumption is a practical approach to alleviate the complexity of natural illumination. Under this assumption, we consider that the original image with pre-baked lighting is a purely diffuse surface, thus, we can effectively ignore its original lighting conditions. We also need to overcome the lack of HDR information. As shown in neural illumination, employing an intermediate LDR to HDR image translation task in the end-to-end model increases performance. We use an autoencoder to translate the relit Matterport 3D images to the HDR domain prior to regressing their lighting. Finally, we overcome the limited pool of available HDR lighting maps by blending uniformly sampled HDR maps process, increase the variance of our synthesized lightings. Our model's building blocks comprise data synthesis, dynamic range translation, and spherical harmonics coefficients regression. Spherical harmonics transform any signal to the frequency domain in spherical coordinates, as the Fourier transform does in Cartesian. They form an orthonormal basis on the sphere, and thus, each function can be represented as a linear combination of a set of basis functions. The spherical harmonics coefficients are calculated via a projection function and can be used to reconstruct the signal, with lower orders representing lower frequencies. Our concept relies on previous works for precomputed radiance transfer and irradiance maps. The first three orders are a very good approximation of the surface's irradiance, given that irradiance smoothly varies with orientation. In addition, under distant illumination, the lighting operation only depends on the surface's global direction and can be efficiently calculated using a matrix vector and vector-vector product. The resulting differentiable relighting operation can relight spherical panoramas when normal maps are also available, allowing us to synthesize new samples with various lightings. To increase the variance of our data synthesis pipeline, we linearly blend randomly sampled HDR lighting maps and then reproject the blended HDR map to a new set of coefficients, using these to relight input images. By mixing lighting's parameters, we greatly increase the variance of our input lightings. Our data synthesis block generates relit samples with highly varying lighting. Regarding the dynamic range translation, we train a UNet-style autoencoder using the neural illumination dataset of coupled LDR and HDR images. It is supervised with two reconstruction losses, on the raw HDR image and on its low-frequency representation of it after projection and reconstruction. This module is trained separately, and its parameters are then frozen, with its output fed to the lighting encoder, which regresses an RGB spherical harmonic representation of the estimated lighting. We impose a prior on the predicted spherical harmonics coefficients, taking into account that higher frequencies correspond to smaller values, as evident by the Laval dataset's mean coefficients. Then we use a Derringing low-pass filter on the predicted coefficients to eliminate ringing artifacts. For each training sample, we first sample two HDR maps, blend them and estimate the blended coefficients, which are used to relight an input LDR, which gets fed through the pre-trained LDR to HDR image translation model, with the resulting HDR image fed to the lighting encoder. We supervise our model with a sparse 1 Lyra coefficients loss and a dense 2 Lyra reconstruction loss. Since our relighting operation is fully differentiable, we can also use it on the supervision end. As we predict HDR coefficients, we first translate the original image to the HDR domain and then relight it with the original and estimated coefficients to eventually use a standard photometric loss on the log-transformed relit HDR images. Our final objective combines all losses in a weighted manner. As all prior work focuses on perspective images, we offer results compared to the work of Barron and Malik that has no restrictions. For a fair scale-free assessment, we report the median scaled RMSE, which shows the efficacy of our data-driven approach. Our loss ablation indicates the importance of photometric and coefficient losses, with the former having the largest effect. Yet, the most significant boost is offered by the spectral prior function that aids the learning process. We offer qualitative results on unseen in the wild samples harvested from the internet. We show perspective crops of the panoramas which showcase how our model can correctly capture lighting in indoor scenes. One advantage of our panoramic approach is that we estimate a scene's global lighting, allowing for placements in the whole scene. Our presented model was trained using uncoupled datasets and image-based relighting as a data synthesis and supervision mechanism. We also showed that imposing a prior spectral distribution on the estimation spherical harmonic coefficients greatly boosts performance. Yet, regressing higher frequency coefficients remain to be investigated, as well as appropriate supervision schemes for detailed lighting estimation. Thank you.